Greetings. In this lab, called the filtering lab, you will get to write a custom filtering function in Matlab and use it to process signals through filters. You will implement both a finite and infinite impulse response filters, that is both FIR and IIR. So let's go ahead and jump in. I prepared some slides for us to look at as we look through this topic here. So let's begin with the difference equation. So the subject of filtering begins with this equation. One of the things I want to point out is if you look at both sides of this equation, you see something that looks very much like convolution. So here on the left-hand side we have some coefficients convolved with the output of the system, which is denoted y. And here we have, on the right-hand side, we have some coefficients b convolved with x, which is the input to the system. And I think it's interesting, if you ever forget what a difference equation looks like, just think of convolution and write the output convolved with some sequence A and the input convolved with the sequence B. Set those equal to each other and you have a difference equation. Note that the number of terms on both sides is finite. We'll let n be the number of terms on the left-hand side dealing with the output, and m be the number of terms on the right-hand side dealing with the input. So think of difference equations as the discrete time counterpart to differential equations. So we're going to do a series of transformations on this equation. Let's take a specific example where we let n and m both be equal to 3. So what I've done is I've expanded out these sums for that special case. So when we have n equal 3, on the left we have terms k equals 0, 1, and 2. So here's the first term, k equals 0, so we have a0 yn, because k is equal to 0, so we have a0 yn minus 0, which is just yn. Then we have a1 yn minus 1, a2 yn minus 2. On the right-hand side, we have b0 xn, b1 xn minus 1, b2 xn minus 2. So that's nothing more than just a simple expansion, writing out all the terms for this special case. Now, usually with difference equations, we assume that this a0 term is equal to 1. If that is not the case, you can simply, let's suppose it's some other value other than 1 and also other than 0. We'll go ahead and divide all of this equation by a0, and then we'll have a unity coefficient in front of yn, and then all of the other coefficients scale. So let's just assume that a0 is equal to 1. Then we get this difference equation. Now, the reason we wanted to eliminate that first coefficient is because we want to solve this equation for y of n, and we don't want to worry about that first coefficient. So what we're going to do is bring this a1 yn minus 1, a2 yn minus 2 to the other side of the equation over here. Now they appear as minus a1 and minus a2. And we've solved for y of n. This gives us a recursive equation. I've repeated that equation right here at the top of the page. This is a recursive equation. It's a forward recursion. So if we know what the, let's just look at this for just a second. So there's two parts here. We have a part involving the input signal, which is x, and we have a part involving the output signal, which is y. And if we look at these terms for just a minute, we have the current input. Since the output is being computed at time n, we have the input at time n, and then we have the input at the previous time, n minus 1, and the input previous to that, n minus 2. Then when we look at the other terms here, we have yn minus 1. That's the output of the system at the previous time, and yn minus 2, again, the output 2 steps back. So this recursion involves these terms that we're going to call the feed forward. This describes how the input signal is used to compute the output. And then we also have some terms that are called feedback terms, where we're taking previous outputs and using those to feedback and calculate the current output. Notice that to calculate the output at time 0, we would need to know the input at time 0, but also the input at time n minus 1 and n minus 2. and the output at time n minus 1 and n minus 2. So it involves knowing some initial conditions like what you'd find with differential equations. Normally what we do is assume that all previous inputs and previous outputs are 0, which is equivalent to basically assuming that these are causal signals. Now, if we repeat those steps for the general case, not for the simple 3-term case that we were looking at just a minute ago, notice we can do the same thing. We can assume that A0 is equal to 1. We can solve this equation for y of n, and we get these feed-forward terms that you see here showing up in the blue box, and then the feedback terms. Notice that this sum starts with k equal 1 instead of k equals 0. Because we pulled out the k equals 0 term, that's where this y of n comes from. So here the lower limit is k equals 0 up to m minus 1, and here the lower limit is k equal 1 up to n minus 1. So this is the difference equation that corresponds to an infinite impulse response filter. And if we just throw away the feedback terms, which is what we do now, then we get a finite impulse response filter. So infinite impulse response means you have feedback. Finite impulse response just simply means there's no feedback. The output is just a linear combination of a finite number of inputs. So let's look at some machinery on how we would use to implement this FIR case, finite impulse response filter. So what we'll do is we'll have 2 arrays of numbers. The first array will hold the impulse response. In this case, the impulse response has these 6 values, H0 through H5. And then next to that, we'll create another array in memory in our program to hold the samples of the input signal. Initially, the values are all initialized to 0, which corresponds to our assumption of a causal input signal. So right here at time 0, we have this new sample called x0 that shows up. And what we're going to do with that is put that into our data buffer. So the first row of this table shows what the data buffer looked like, or the data array, at time t minus 1 where we initialized it. And then here at time t equals 0, I'm showing what that array looks like at time 0. When the first input sample shows up, x0. And the way we operate on this array is we shift all of these values over 1 to make room for the new input sample, which we write into that first array element. Notice that the last array element is overwritten, essentially thrown away, as we write these new samples in. I'm describing this as the shift old data, step 1, insert new data, step 2. And then the next step in the process is to form a sum of products. So what we do is we multiply H0 times x0, H1 times 0, H2 times 0, and so on, form all of these products, which is what you do in a convoluted kind of a situation. And then after multiplying, you add all of those terms together, and that gives you the output at time 0. Notice that we're dealing with an input at time 0, and that after we processed all of the values, we get the output at time 0, the same time as the input. And we repeat that process over and over again. We shift these values over to the right in the data array, shift in the new value, x1, and then we multiply the impulse response times the data, add all the values up, and we get our scalar output value, y1. And this process just repeats. We shift and insert the new data, and we multiply the arrays together and add the products. Okay. And we just keep repeating this process over and over and over. Now, before we go any further, I want you to just think about what the data array would hold at time n. Previous to this, we would shift over all of this data, and we would insert this new sample x of n. Now just look at this for one moment. Notice that the indexes decrease as we move from left to right. So here we have xn, which is the current input, xn minus 1, that was the input that we received the last time around, xn minus 2, xn minus 3, and so on. So the input signal in this example is written in time reversed order as we move from left to right. The impulse response, notice that it appears in natural order, with the index increasing as we move from left to right. So this corresponds to this idea in convolution where you flip and shift one of the signals, either the impulse response or the input signal. In this case, we're leaving the impulse response in natural order, and we're doing a flip and shift on the input signal. So now the question is, now that you've seen this mechanical type machinery operating, the question is, could you implement this in a computer program? So let's just see how we might do that. We want to write a function called myFIR where we pass in the coefficients, the filter impulse response B, which are the difference equation coefficients for the FIR case. And we want to pass in a scalar value called x. This is the input signal, the current sample of the input signal. So remember that for a filter, we need to have some persistent memory that exists from one call of the function to the next. We could allocate that memory outside the function and pass it in, but that's kind of a pain. We want a nice clean interface. So Matlab has this built-in capability for persistence of variables on subsequent function calls. So if you declare these variables as persistent, we'll have an array called Z, which is the data buffer, the data array, and L, which is the length of that array. So notice that on the very first time we call this function, we say if Z is empty, in other words, if Z is an array that doesn't exist or has nothing to it, we're going to let L be the length of the impulse response array, which is B, and then we will allocate an array of zeros of size equal to the size of B. So we're initializing our buffer to 0, and then we're going to do the shift. We talked about this previously. So I'm going to write a for loop to do that shift, and the for loop will go from n equal 2 up to n equal L, which is the second element up to the last element. Now look at what we're doing here. I'm saying, and this is the shift, because I let something at index 2 equal something at index 1. And then something at index 3 equals something at index 2, and so on. But if you write your for loop like this is just a little word of warning, there's going to be a problem. Because notice what's happening here. We set Z2 equal to Z1, and then Z3 equal to Z2, but Z2 is already equal to Z1, so now Z3 is also equal to Z1. And if we repeat this process and carry out the for loop operation, this leads to an array that is constant. We've moved all of the values in the array, but we did it in the wrong order. We started at the beginning of the array. What we should have done is start at the end of the array. So we're going to write a for loop that decrements the index instead of increments the index. Everything else is the same, and it's going to work out. So let's just see this. So suppose L is equal to 5. So we set Z5 equal to Z4. Z4 equal to Z3. Notice that we're not overwriting anything. Well, we're not overwriting anything we want to keep here. So by starting at the end of the array, let's just go back to our picture. Notice that, say, for example, in going from line 5 to line 6, we first shifted x1 over and then shifted x2 over. But if we had processed this array in forward order, we would have written x5 over to x2, but then we would have written x5 again to the next slot, and etc. So anyway, if you just write this out on a piece of paper and take a look at it, you can see that we need to process that array in reverse order. Okay. The next step is to insert the new sample into the first element of the array. That's what's happening here. And then finally, we can do the multiply add. So if we initialize an accumulator to 0, we can just run a for loop over this thing and say multiply the coefficients times the data, add it all up, and we're done. We can just return that y value from this function. So this is a first cut at what the FIR filter function should look like. what this does is it for given one input sample, it calculates one output sample. Now, the question that I have for you here is, can you write this using only one for loop? So that's kind of the assignment. Now that you've seen what the machinery looks like, can you write this with just one for loop? You know, having two for loops here is inconvenient. Can you both shift and do the multiply accumulate in one for loop? So that's the assignment. Figure that out and try and get that done. Okay, next we're going to move over to the infinite impulse response case. So let's go back to that recursive form of the difference equation where we write the output in terms of the input, linear combination of inputs, minus a linear combination of past outputs. If we map this onto a block diagram, this is what this diagram would look like. And I want to make a few quick comments here. This z to the minus 1 block will become more clear later in the semester, but for right now, just think of this as a single sample delay. If you notice what this block does, it takes x of n as its input, and the output is x of n minus 1. So it's delayed by one sample. Similarly here, this block has xn minus 1 going in, coming out xn minus 2. So z to the minus 1 does a one sample delay. These triangles here, these that look like little gain blocks with labeled coefficients on them, those are just multiplying the signal here, xn by b0. So coming out of that triangle is b0 times xn, which is the first term that you see here in the difference equation. Coming out of this gain block here is b1 times xn minus 1. That's exactly what we need for that second term. And then these adders just add all of these pieces together. Let's look at the output. Y of n minus y going into a block gives us yn minus 1. This was available last time. In terms of our software that we're going to write, we have the previous output available from the last time around. What we're going to do is multiply that by the coefficient. Notice that's negative a1. And then we're going to add that to the other values that we're computing here. So this is basically just a block diagram that represents this difference equation written in recursive form. And I think I just explained this. We have a feed forward part. You can see that all the arrows are moving forward here. And there's the feedback part. You can see that the arrows are pointing in the negative direction. So we call this feedback. Yeah, but the bottom line here is that the structure of these two sections is very similar. There is an array of samples of data. There's an array of coefficients that are multiplied by that data, and then you add everything together. Same on the output side. We've got an array of samples times an array of coefficients, and we add all those things together. So in terms of programming this thing, we would program it a lot the same we would the IIR case. So we can write a Matlab function called myIIR_filter. In this case, we're going to pass in an array of feed-forward coefficients B, feedback coefficients A, and one scalar sample of input signal X. And we'll return one scalar output sample Y. So we go through our persistent block that just allocates memory and keeps track of some variables for future use. We do our shift on the input signal. We do a shift on the output buffer here array. We insert the new input signal, and then we have a couple of for loops that do the multiply and accumulate, or for the feed forward part, and for the feed backward part, we do a multiply and subtract. And then when we're all done, we save the output value in the array so that the next time around it's available. So that's an example of an IIR filter function. Your job is to, again, try to implement this with just a pair of for loops, one that works on the feed forward part, and one that works on the feedback part. I think that's the end of my slides. Okay, so what I'd like to do now is to jump over to the lab and talk about a couple additional things here. So I've already talked through all of this stuff. This is a picture that's probably useful to pause on. This kind of lays out the IIR filter case slightly differently. We have an array of coefficients here, an array of data for the feed forward part, and then for the feedback part we have the same type of situation. When it's time to compute the output, We multiply all these numbers, these two arrays together, add the values, multiply these numbers together, add the values, and then we can get the output y of n. So I don't know, that's another view that I haven't shown before, but probably useful for thinking about how this filter works. Yeah, the next thing that I want to introduce you to here in this lab is filter design. Now, we haven't covered enough material so that you can be an expert on filter design, but for right now, I want to just hand you a recipe that you can use for designing filters, low-pass filters at least. And the recipe is given right here. You can see that it starts by choosing a passband edge frequency and a stopband edge frequency. Those would be in units of hertz. The very first step is to normalize those frequencies by dividing by the sample rate, Fs, which you will know in whatever problem you're working. And then we'll do an additional transformation on these frequencies. We'll calculate the sum and divide by 2 and the difference and divide by 2. That gives us two new frequencies, F1. And this should be F2. That's a typo, which I should go in and correct. But once we have F1 and F2, we just need to select the order of the filter, which has to be an odd integer. And from the order, we can calculate this L, which is the half length. And then there's some Matlab code down below that you can use to construct the filter. But what I want to point out here is that this filter is a product of two sinc functions. There's a narrow sinc function, which is the one on F1, and a wide sinc function, which is on F2. And that's the impulse response. Here are those transformations. You can see here in the code that the correct subscript on this frequency F should be F2. Notice that's right here. F2 is the difference divided by 2. This just shows how you can implement that. Notice that sinc functions have this property that you divide by 0, and so this basically goes in and fixes that middle sample so that we don't have to worry about that. And the rest of this just calculates the frequency response and makes a plot. Here is a plot for a filter designed to pass up to 1,000 hertz and stop from 1,500 hertz and above. And you can see what the frequency response looks like. You can see it's fairly flat in the pass band, has a gain of 1. And it's fairly flat in the stop band, has a gain of 0, pretty close to 0. And this band between 1,000 and 1,500 is called the transition band. This is where the filter rolls off from the response of 1 in the pass band down to a response of 0 in the stop band. You might be wondering, well, why does it work this way? And I'd like to just quickly try to explain why we get this kind of response. So for this, I'll shift gears and come over to a quick little sketch. Essentially, what we're doing is we have the product of two sinc functions here for our impulse response. And if in the time domain we're multiplying two signals together, what we're doing in the frequency domain is convolving two signals. So what I want to do is just illustrate this convolution. So the Fourier transform of the first sinc function is a wide rectangle, and the Fourier transform of the second sinc function is a narrow rectangle. And you can imagine that when we convolve these two, remember this is in the frequency domain, when we convolve these two functions together, what's going to happen is right around this frequency where the wide rectangle function transitions from stop band to pass band, or from pass band to stop band, when we convolve this small rectangle by the bigger rectangle, what's going to happen right here is we're going to get a linear roll-off between pass band and stop band. And then in between, it's going to be a constant, and then out here it's going to be a constant. And so that's why the frequency response of this filter, which again we're only showing for frequencies greater than 0 in the picture, that's why we get the shape that we're getting here for this frequency response, okay? That's why it looks kind of like a trapezoid. We'll talk later in the semester about why it's not exactly a trapezoid. You can see there's a little bit of rounding at the corners here, but it's pretty close. And if you want it to be closer, increase the value of n. In this example, I let n be 101. If you let n be 1001, you'd see that this would much more closely resemble a trapezoid. The problem is it's a much longer filter. If we view this trapezoidal filter on a dB scale instead of a linear scale, you can see what the actual ripple looks like in the stop band, which is interesting. We'll have more to say about that in the future. And then here is the impulse response. Again, it looks kind of like a sinc function. It's actually a product of two sinc functions. Now, the next thing that I want to point out is that once you know how to design a low-pass filter, you also know how to design other kinds of filters as well. So for example, let's take a low-pass filter, an ideal low-pass filter, which looks like this rectangle. And if we have another filter, which maybe is an all-pass filter, so again, this is frequency domain. So suppose that this filter up above is an all-pass filter. In other words, its magnitude response is constant, it's equal to 1, it passes everything. What would happen if I would subtract the second one from the first one? Can you see that, when I do that subtraction, I will have 1 minus 0, gives me 1 up to this frequency, and then I have 1 take away 1, then up to this frequency that's going to be 0, and then over here I have 1 take away 0. And so now you see that we have a high-pass filter. So what I've done is I've taken an all-pass filter, which has impulse response equal to delta of n, and I've subtracted from that a low-pass filter, which has impulse response h of n. And so this filter has impulse response delta of n minus h of n. So that's one way you could design a high-pass filter. What if we wanted a band-pass filter? Let me start on a new sheet of paper here. So suppose we took a wide low-pass filter and we subtract from it a narrow low-pass filter. So suppose this is filter impulse response h1 of n, and this down here is filter response h2 of n. The magnitude response, which is what we're plotting here in the frequency domain, is h1 of f, and this is h2 of f. But remember, the Fourier transform is a linear transform, so if we subtract in the frequency domain, we would subtract correspondingly in the time domain. But I think you can see here that if we subtract these two, what we'll get here is between this frequency and this frequency, we'll have a gain of 1. And then here we would have a gain of 0. And then we would have a gain of 1 again out to about this frequency. So this is a band pass filter, BPF. And its impulse response in the time domain is h1 of n minus h2 of n. So once you know how to design low-pass filters, you can combine low-pass filters with other low-pass filters and make band-pass filters. You can combine all-pass filters with low-pass filters and make high-pass filters. You can make band-stop filters. You can make all sorts of different filters. And that's what I illustrate back over here on the slides. Let me shift back over to the slides. Down below. So here's a low-pass filter, H1. Here's a wider low-pass filter, H2. And when I subtract those two, I get a band-pass filter. Notice that this is passing frequencies between about 0.15 and 0.3. And it's stopping these other frequencies. Lower frequencies and higher frequencies it stops, but it passes these mid-range frequencies. So we'd call that a band-pass filter. You can make a high-pass filter. Notice that an all-pass filter is a delta function, And you can take all pass minus a low pass and get a high pass. The one thing that you have to keep in mind when you're doing this adding and subtracting of impulse responses is you have to keep them time aligned. In other words, let's go back to the impulse response picture here. Notice that this impulse response, the peak in the impulse response here appears here at sample number 50. When you construct a delta function, which is an all-pass filter, the impulse needs to turn on at time 50. So basically you have to keep these signals time aligned, and the alignment point for the sync function is the center. Let's just say that for right now. We'll talk much more about that sort of thing later in the semester. And so there's some Matlab code here on the page that deals with this. Let's go down now. Oh, and this is the resulting high pass frequency response. Let's go down now and look at the assignment. I'll just talk about a few things here. We're going to look at a couple of different kinds of filters. The IIR filters that we'll look at are, the first one is a shelving filter. And there's a web page that I made just to talk about shelving filters. I'm giving you here the difference equation so you can read off of this the feed forward and the feedback coefficients. And then you can go off and apply that. This is the frequency response. Why do we call it a shelving filter? It looks kind of like a low-pass filter, but it's not. Because it basically gives gain to low frequencies, in this case 10 dB of gain to low frequencies, and higher frequencies get a gain of 0 dB, which is no attenuation. So what we're doing is we're boosting low frequencies and passing everything else, essentially. So when you run a signal through this, here's a spectrogram of the input signal. This is some audio. Notice the intensity of the low frequencies here. This is the input signal. When you look at the intensity of the output signal, notice that those low frequencies have been boosted up a little bit. And when you listen to the audio, you'll be able to hear that. Let's see. Okay, so what I have done, let's jump over to Matlab for just a minute. Gives me a chance to talk about a couple of things. So what I've done is I've copied the coefficients from this filter. Notice that the feedback coefficients are going to be 1. So don't forget the unit coefficient in front of yn. And then the coefficient of yn minus 1, if we bring that back to the other side, remember you have to write this, you get the coefficients from the standard form, not from the recursive form of the difference equation. So we have to bring these y terms back to the other side of the equation. That will change their signs. So when I show you the coefficients in Matlab, you will see these appearing, this one with a minus sign, this one with a plus sign. And then over here we have the feed forward terms, 1.008, 1.978, and so on. So let's jump over and take a look at those in Matlab. So here we have the feed forward coefficients, B, the feedback coefficients, A with the appropriate sign. Notice that the lead coefficient is 1 by assumption. Here I read in the audio using the audio read signal or function. That brings the data into a variable called x in the workspace and the sampling rate into a variable called fs. One of the reasons I wanted to talk about or go through this is I wanted to introduce you to another function called freqz. We'll go into more depth later in the semester on exactly maybe what's going on inside. For right now, what you do is you pass in the feed forward coefficients, the feedback coefficients, you pass in a scalar that tells the function how many points you want in the output, and then you pass in the sampling rate. It returns a complex array H, which contains both the magnitude and the phase in it. So we'll just use abs to pull out just the magnitude. And it returns an appropriately scaled frequency vector that you can use for making your plot. So notice that the next line of code here is I say plot f, comma, 20 log base 10 of the absolute value. That's going to give me a dB plot of the magnitude response. I set the x limit to 0 to 3,000. The sampling rate is like 40,000, so I don't want to see all of those frequencies. I just want to focus on the lower 3,000 hertz. and do some other things. So let's go ahead and run this in Matlab. So that's lab filter, I think is the name of it. Okay, so what that does, you can see here, is calculates the magnitude response. This is the shelving filter. You can see the magnitude response here. And the reason that this is different than what we've done in the past is that in the past we have had the impulse response. Remember that the frequency response is the Fourier transform of the impulse response. In this case, we don't have the impulse response. We've got this difference equation. The difference equation is not the impulse response for IIR filters. So yeah, this freqz function does some magic on the difference equation coefficients and returns the frequency response. And again, we'll talk later in the semester about what's actually going on under the hood. For right now, you can use that function to calculate frequency response for difference equations. Let's see. Let's go back now to the slides. So that's a little bit about shelving filters, and we're gonna implement this shelving filter in this lab assignment for the programming part. The second thing that I want to teach you about is notch filters. This is the magnitude response for a notch filter. You can see why it's called a notch, because it passes everything with a gain of 1, except for a very small band of frequencies that fall in this notch in the response. In this case, I designed this filter to have a notch at 800 hertz, and you can see that it does a pretty good job removing any signal at 800. So a notch filter would be used to remove some kind of a sinusoidal signal from that you don't want to have. And here I'm showing you how to calculate or basically giving you a recipe for calculating the feed-forward and feedback coefficients in the notch filter. I noticed just as I was looking at this that there's a typo here. This A squared should be Q squared. And where do you get Q from? Well, you calculate it like this up here in the recipe. So I know a little bit of this is kind of black box, you don't know why or what's going on. Again, when we get to filter design, you'll see why this works. I don't want to wait till filter design because that's sort of a topic we touch on later in the semester. So there's a lot that we can do just by using recipes for right now and practicing implementing. This is really what I want you to do right now, is just getting used to write your own filtering code and using that and applying it to signals and see what the effect is right now. Okay. Yeah, so here we are in the assignment. Let's see, I think there were a couple of things I also wanted to show about the, yeah, let's run this. So when you design the notch filter, yeah, let's see here. Okay, when you design that notch filter, you're going to take that and apply it to the Firefly intro signal that we worked with in the first computer assignment. And here I'm showing you the spectrogram of the input signal on the top, and down here this is the spectrogram of the output signal. Again, this is a notch filter, and it's been designed to remove any frequency in the input signal that is at 466 hertz, which is this particular note that you can see appears here repeatedly in this song. You can see here, it appears here toward the beginning. It just appears multiple times throughout. Now, if you look at the output of this notch filter, wherever you saw that note in the input signal, you can see it's essentially been removed in the output, leaving everything else unchanged. To see that up close, let's zoom into this chunk of the signal right here in both of these. Okay, so here is the input signal. You can see that we have this note here, this note, this one that's going to get removed, and then this other note. Notice that down below in the output signal, the original notes are there, these notes that shouldn't have been touched, and then the note that fell in the notch is essentially removed. So now you can see that, and if you look across, that notch filter did a pretty good job suppressing any occurrence of that note. So it looks like it worked. All right, let's jump back into the assignment. Let's just sort of step through the parts here. So the first thing is to write the FIR filter function, use a single for loop. Try and figure out how to do it with a single for loop. And then I'm going to give you an impulse response, and I ask you to put this input signal in. Put in 1, 0, 0, 0, 0. This is how you're going to test your code to make sure it's doing the right thing. This is an impulse. So when you put an impulse, the sequence 1, 0, 0, 0, 0, that's an impulse. If you put an impulse into an FIR filter, you should get out the impulse response, which is H. And so this is a way you can test your filter to make sure that you've written it correctly. If the output sequence is 1, 2, 3, 4, 4, 3, 2, 1, then you have a pretty good feeling that that's going to work. Next, I want you to take this impulse response and put that into, use that as the filter impulse response, and put this cosinusoidal signal into the filter. Put in about 20 samples and look at what comes out. Also look at the frequency response, and that will give you a clue as to why you are observing the output that you observe in this case. And finally, you use the freqz function to make a frequency response plot. I also ask you to design a band stop filter using combinations of low-pass filters. We talked a little bit about that here. Hopefully you'll be able to pull that off. Then we move on to the the IIR filtering. Again, write the IIR filter function and then use it to apply the shelving filter to the audio signal. And then finally, design this notch filter and apply it to the audio clip, the Firefly audio clip. And that is everything. So if you have questions about this, please write to me on Slack or send email, and we'll get things figured out. Thank you.